Okay, so first of all, as we start this section, remember our whole theme for this time around is going to be on figures like this, either triangle, rectangle, prisms, whatever. So the purpose is for us to review on how to find the volume, how to find the area, such things. I think it's been a long time since you've seen this anyway, so it's actually quite good. So let's take a look. So let's express the volume of this rectangular prism as a monomial. We already talked about the difference between a prism versus a pyramid, right? And the easiest way to demonstrate that is try to test it yourself. A pyramid, the reason we call that a pyramid is because of the pointy head. And if you take that pyramid and flip it upside down, what will happen? It will tip over and fall. Okay, there's no balance, and the reason because the base and top, they're not identical, right? Versus a prism, if you look at the prisms, we have identical base and top, so therefore it doesn't matter if you flip it upside down, it will still going to be able to stand. That's the main difference between the two. Now, we talked about volume before, and volume of this rectangular prism is going to be what? What is that? See, always, to solve something like this, always start with, okay, well, if they're talking about volume, can we write that basic formula out first? What is the volume of a prism? Rectangular prism. Yes, Anna. Length times width times height. So I'm just going to go ahead and identify that the volume is length times width times the height. Okay? So now that we have that, please understand that we're getting to a point where I don't just give you, okay guys, the length is 5, the width is 2, and the height is 7. Not the case anymore. It won't be that easy, right? But you can certainly make it that easy by making connections, guys. All you need to know is, well, I don't care what length is at this point. I can throw a horse in there if I want to. A horse? Doesn't matter. But in this case, I'm actually throwing what we call a monomial. Now, you don't know what a monomial is. Don't worry. We'll talk about that. But look at your rectangular prism right here. Where's the length? Do you see it here? The bottom. Fine. We call that the length. That's fine. But technically speaking, the length would be either one. I don't really care. If you call y to be the length, then so be it. Then the other one has to be the width. Doesn't matter. So length and width could be used interchangeably. So now let's call the length to be this particular monomial right here. And the width, of course, is going to be the y then. And the height has to be what? Okay, this one, right? All right, and we know that it's length times width times height, so we have to do some substitution on this. So let's substitute. Volume is, the length is x times y to the third. Okay, that's the length. The width is y, so I'm just going to go ahead and write y in there. And the height is? X squared y. Okay, x squared y. Okay, so this is what I have here for this particular problem. And I'm like, okay, wait, it looks pretty complicated. It's a mess. Everything is kind of out of order in a sense. When I say orderness, we're talking about rearranging the terms, rearranging the variables so that, what I say is, make it, sort them. Make them neater if we can. Okay? Just like how we have different shapes of blocks, and when your teacher asks you to, put them, clean up. Then you say, oh yeah, all the square blocks will go in this bucket, and all the circles will go in the other bucket. Kind of like that same deal. When we see something as a mess, we clean it up. In this case, we simplify. In this case, I'm like, wait, how do we simplify this thing? We don't have a rule or a way to do this yet. Usually, we have an established rule in class. You put all the square blocks in this box, red box, whatever. Now we need to establish a rule here in this class as well, or in this case, for this particular problem. And that will lead us into our first session here about multiplying monomials. So how do we get that part? First of all, we need to understand what is a monomial. Let's write that down. What is a monomial? First of all, if I break that two terms out, that word, mono, have you ever heard of that term before? Mono?
In soccer, you use your hands.
Mono is a disease? Mono means what?
One.
One. Thank you. Mono means one. Mono. Okay? What about the word meal? Have you heard of that?
Delicious.
Maybe not, but that's fine. But the word meal means term. One term. One term. Now we talked about terms in the past. How do we separate terms? Do you remember? How do we separate them? Adding or subtraction. Yeah, exactly. So that's how we tell, or how we count terms anyway. For example, I give you something like this. you know that this particular expression has how many terms? Two, because it's separated by a plus or a minus. That's how we separate the term. But in this case, we're not talking about two terms. We're talking about just one term. A monomial is just a one-term expression. Now, so what's that basic definition of monomial? Well, first of all, a monomial could simply be just a number. That is considered to be a term. Just a number. I throw you a 5, that's a term. That's fine. Or it could just be a variable by itself. That is considered to be a term as well. A number or a variable. So for example, I can throw like this. Yeah, that's a term. Fine. That's a term. You only see one of them. That's a term. Or I can just give you this. That's a term. Okay? Now here's the next part of this. It's a number or a variable or a combination, well, you know that, it's coming, of number of a number or numbers and a variable or, once again, multiple variables as well. You can have multiple variables. And this is the key word right here. Linked up by multiplication. Has to be multiplication, guys. This is the glue of all monomial terms. This is how they hold this is how monomial term is being held together. This glue we call multiplication. The glue that glues everything together. So for example, even though right now, if we write like this, we have two terms, right? But if I decide to remove that and link it up by multiplication, it's 5 times y, and guess what? It's one term. It's a monomial as well. You see it? That's a monomial. It's a combination of numbers and variables, fine. Or it could be multiple variables and the same thing, but as long as everything's being glued up by multiplications, a number is being glued to other variables by multiplication, we still consider that to be called a monomial. For example, I can have something like this. That whole thing looks pretty long, right? It still is considered to be one monomial. One term. Because remember I told you that a term is being separated by plus or minus. Do you see any plus or minus here that separate the terms? No. Everything's glued together using multiplication. So therefore, this whole thing is one monomial. I don't care how long it is, but as long as it's being glued by multiplication sign, is one whole monomial term. Any questions so far? So never ever, there's no division involved. Okay? Division doesn't glue the monomial term. So for example, if they give you something like this, it might be misleading at first, but think about this for a moment, okay? If I have something like this, is this still a monomial or not? Is it not?
Yes.
Even though there's division involved, but think about it carefully.
No, because multiplying that by that thing.
So technically speaking, what's 4 divided by 2? It's a 2, still a number, isn't it? A number divided by a number is still going to be a number. Whether it's a decimal or a fraction, it's still a number, right? A fraction is still a number. But notice everything's still being glued up by multiplication. So you're asking, well, when is it not a monomial then? When will it be something that's not a monomial? Well, this is the case where it's not a monomial. Watch this. If I have something like this, and you should make this into something that you make a note of this. But we will never ever have variable in the bottom, ever, to be called monomial. So if I ever give you something like this, why is it not a monomial in this case? Because you are using what to glue the y together, to glue the y to the rest. Division. Division to glue another variable to it is not allowed. See, you cannot take x divided by y, do you? You don't know what it is. It's okay to take 6 divided by 6, that's fine, because a number divided by a number is still going to be a number. So you still manage to do away with the division for a number. but you cannot get rid of the division for variable, can you? You see it? If you manage to dissolve the division sign along the way, then that's still technically going to be a monomial. But if it's going to stay there for the rest of the term, won't be a monomial at all. Okay, yes?
So like if it was 6 over 3, 6.
Let's say if I give you something like this, okay? 5/10. Can you dissolve the division sign? Can you write this without division? Yeah, it's going to be what? 0.5, right? As long as you can say, I can do that, I can get rid of the division, then it's good. But if you're stuck with division, not a monomial. Does that make sense? So the reason this is not a monomial, for example, is because, for example, I can resolve 5 over 10, which just makes it 0.5. But can you dissolve the x divided by y? Cannot. The division sign can still get stuck there, isn't it? And therefore, this is not a monomial. Okay. It has to be a multiplication to glue things, not division sign. Okay. Any questions so far? We're good? All right. So you understand the basics of what a monomial is. Then I'm going to give you a very basic example so you can actually understand what's going on. In the past, we learned that, by the way, what is the answer to this, Rob?
8.
Who thinks 6? Is it 6?
No.
No, it's not. What's the answer?
8.
It's 8. Well, we take 2 times 2 times 2, right? That's easy. Can we write this in another way? A shortcut of this?
Yeah, 2 cubed.
Oh, 2 cubed. Ah, so you learned about this before. This 2 right here is called
Base.
the base, okay? And the top number right here?
Exponent.
It's called the exponents of the power, right? So this is pretty easy stuff. Exponent, power, base. We learned this. Please, this is like the most common mistake on your test. I don't know why, but people always do this. When I say 2 to the third, I meant to say 2 times 2 times 2, right? In your mind, you also force yourself to say something like that, but then when you write the answer, this is what you wrote. 2 to the third power is 6. I mean, you should ask yourself and question yourself too and say, wait, if Mr. Wing wants me to get this power to be 6, shouldn't he just, write 2 times 3? Why would he write 3 on the top of 2, you know what I'm saying? So think carefully before you start writing your final answer. So obviously this is not the case. 2 to the third means 2 times 2 times 2, or 8. Questions on that? I'm going to do a couple problems and see if you can actually see a pattern so that we can establish what we call a cleanup rule for monomials. Okay? So imagine if I have the following. So let's say I have that. What do you see here? This is too long, right? I don't want to have to write a whole bunch of 2's. But clearly, you see that this is 2 times 2 times 2 times 2, which becomes 16. And this is 8. And since they're all multiplying, technically they're all considered to be one monomial, isn't it? Like that by multiplication. So 16 times 8 is 128, you said. And indeed it is 128. Now, if you don't believe me, you certainly multiply it yourself. Now, we know what the answer is. It's 128. We multiply everything together. But sometimes you want to write it in a cleaner way possible using base and power. So in this case, 2 times 2 times 2 times 2, how do you write that in a compact way? Yes? 2 to the 4th. So basically we count the number of 2's that we have. So if we have 4 sets of 2, that's why we say 2 to the 4th power. 2, I have 4 sets of 2. That's what it means when you say 2 to the 4th power. I have 4 sets of 2. So you write 2 4 times. Over here, how many sets of 2 do you have?
3.
3. So don't you write 2 to the 3rd? Right?
Yeah.
2 to the 3rd. And notice that the power, I hope you notice something, but how many 2's do you have here if you count them all?
7.
7. Interesting. I wonder what...
You can add the...
Oh, we can add. Interesting. 7 of them? And notice how the powers are technically the same thing. Number, if you add them, 4 plus 3, 7. So if you... Remember, we're trying to establish a cleanup rule for this? And the way to clean this up, to make it simpler, is to combine them if we can. And notice that these two have the same exact base of 2. We can only sort when they have the same thing together, same common thing, right? Like blue block in one pile, red blocks in another pile. So it must have to share that same base in this case. So 2 to the 4th, 2 times 2 to the 3rd, you can certainly expand it. So we see this. And if we want to clean it up, we put them together. In this case, what's happening to the power in this case? What do you think? We add them. So can we just simplify this whole thing and make it 2 to the 7th power?
Yeah.
And we know that 2 to the 7th, if we expand, we got 128. So the first rule, the cleanup rule that we just established here is that when we have same base, meaning like same blocks, okay, and we have a whole bunch of blocks together like that, we just put them together. So basic addition. Okay, I have 4 of the 2 blocks, and I have 3 of the 2 blocks. I put them together, I have a total of 7 of the 2 blocks, right? And that's what's happening. It's kind of like same kind of deal. So this is just cleaning up work that we have to do, make it simpler. Okay, let's try another one. Okay, I can certainly do something like that, but in your mind, let's translate this in your mind. How many 5 blocks do we have here? 6 of them. And we have on the other one, we have how many 5 blocks? 5 of them. So clearly we have how many blocks total? 11 of what block? 5. And so we know, we just established that rule. If you can expand it yourself, you certainly see like something like this. If you want to write like that, right? We can. And you can count them off if you want to. Clearly you see 11 blocks. But the quickest way to do it is just add the 2 powers together, which becomes 5 to the 11, right? There it is. That's how we clean up our exponents. Questions on that one? Okay, try this one. Can we clean this up?
No.
Why not?
Because they're different.
Yeah, they're different blocks. Cannot put them together. Okay, so in this case, well, by the way, is this still monomial though?
Yes.
It is, linked up by multiplication. So technically, it is still monomial, but we cannot clean up because they are different. We can only clean the same blocks. Okay, any questions so far? Basic understanding. What about this one? What if I have layers of blocks? I have 5. I'll make it a little bit smaller for you here so it's easier to calculate. But what if I have something like this? What does it mean now? What's the difference between this versus this? Okay. Now clearly, how many blocks of 2 do you see here? You expand them all. 8 of them. But here, think about this. How many blocks of 2? Notice how we have double, it's like layers of powers. I say, how many blocks of 2 do you see in here? 3 inside. So technically speaking, we see 3 inside that, right? And then that 5 outside, a power of 5, means how many sets of that inside do we have?
5.
It's like one set inside another set kind of deal. You see it? 40. So in this case, we would have 2 times 2 times 2. That's one set. But how many sets? 5 of them. It's okay to actually write it out. You just test it yourself to prove it to yourself that that's what's happening. And then if you really count them all, 3. So how many sets of 3 here?
5.
5. So how many 2s total?
15.
15. So in other words, this can be simplified as 2 to the 15th power, right? Is that true? But can you relate the power to what you have up here?
Yeah.
What are you doing in this case? You multiply in this case, not adding this. But you can clearly see that when you expand everything out, you're still adding them all up, right? But in this case, we remember we're trying to find the simplest way possible to get to the bottom of this, right? So when we peel layers of powers off of the base, notice how what's happening? We're multiplying them. So I don't care how many layers of powers I have, the general rule is I just multiply them all. Versus this one, I'm not peeling any layers. I clearly see that I have 3 of 2s, and I have 5 of 2s. Together I have a total of 8 of 2s. This one is a bit different. I have 3s of 2s inside, but I have 5 sets of those. You see it? And I can keep on doing that to prove it to myself it works. But now we know a better way to do it. We just when we see layers of powers, we multiply them. Easy. Okay, so now if I apply this and give you just, the following. So that, instead of doing layer by layer, what can you now say? Yeah, well, think about this. I have x times x, right? That's inside. I'd have 3 of them. Is that true? And then I have 5 of these. You can do that, or what can you say now?
You can
You can just multiply them all, which is?
30.
See it? That's the easiest way to do it. You can certainly show it step by step, or you can just do a shortcut on it. Any questions so far?
You look like
Questions?
No.
Okay, if you have no further questions, then I want to go back to our previous problem. See if you can actually answer this now. Alright, remember we want to do some cleanup work, right? Do we have to peel any layers of power? No, we don't in this case, right? No power to peel. But we know we have to do some cleaning up work on this. We have, oh, by the way, if I don't see a power on top of a variable, what is it automatically? It's 1, so I would definitely going to write that to remind myself that there is that first power. So let's clean up the x. What should you say about the x?
X cubed.
X cubed. Yeah, I have 1x right here, 2 more x over here. That's 3x, right? Or I have 3 sets of x. And y is what? Yes. Y to the 5th. Right? 3, 4, 5. Done. What do you think of that?
Is that in this whole chapter?
Pretty much.
Okay, then that's easy. I did that last year.
Okay, good for you.
I got good grades on that.
Okay. Well, but anyway, questions so far in this one? Alright, let's test out one more time before I give you your quiz. But take a look at this. Check that one out. No, it's not. First of all, is this considered to be one whole monomial? Or is it? Yes. Okay, are they all being linked up by multiplication?
Yes.
Indeed. So it's still one whole monomial. So that means we can actually simplify. Clean up, please. What can we clean up? Oh, let's clean up the number first. This is, remember, they're all linked up by multiplication. So when you do that, it's multiplying, right? 6 times 5, 30. Okay, so we cleaned up the number. What else can we clean up?
X to the 5th.
The x. Ah, x to the 5th. And?
Y to the 8th.
Ah, we done it. What do you think of that?
Easy.
You want to make it harder?
Yeah.
No.
Let's do that.
Yeah, go.
All right, here we
Go.
go. Of course. Look at this one.
Easy.
No, it's not the quiz. I'll tell you when the quiz is, okay?
Shh. Relax.
Is that recording?
Oh my god. Yes, it is recording.
You guys are
Okay.
arguing.
First of all, here's my question for you. Is this big thing a monomial?
Yes.
Yes.
Why?
Because everything is being multiplied.
They're all linked up by multiplication. Very good. But what else did we learn today?
The exponents on the outside of the stuff.
Layers. Okay, we just learned about layers.
Yeah.
Okay, in this case, what do we learn? Well, what can we? How we? Okay, so let's peel off all the layers first. What can we say about this first part of this monomial? Okay, so first we know y is to the 9th, but is it only applied to the y?
No.
That's the thing. You see how if you have y to the 3rd and you have 3 sets of those, then that means you will have also 3 sets of the x and 3 sets of the 2. You see how it works? It's like 3 sets of everything inside.
So it's gonna be like distributed property somewhere.
Ah, thank you for making that connection. It is kind of like that. So in this case, we have 3 sets of 2 and 3 sets of x 2. So is it kind of like that?
Oh.
So let me just go and simplify that and show that to you. Is that what we're seeing? I have 3 sets of everything inside.
Yeah.
Over here, what do we have?
3 to the 2nd power.
2 sets of everything. So 2 of sorry, let's write that.
3
3 to 2.
Just squared.
Okay.
X third power.
I have 2 sets of the x to the third. What else?
Y to the third power squared.
Okay. Now can we do some more cleanup work? What is this going to become? 8.
Dude, just stop reading.
Shh.
X.
What's this?
6 power.
Okay.
Y to the 9
Okay. Over here.
times 9.
Uh-huh.
X to the 6.
Okay.
Y to the 7.
7 or 10?
10.
Also 10.
Remember we have 2 sets of that, right? So y to the 10. Can we do some more cleaning work?
Yeah.
Yes.
What?
You add.
Add?
I
There's
mean,
such thing as adding?
No, I didn't.
Okay.
I mean the exponent.
Combine
of
them.
The y.
What is this? 8 and 9 going to do?
17.
72.
Oh. Haha.
Two.
Shh. Think. Is there an addition here?
No.
No. See it? The reason we're adding exponents is because we found that pattern. That's why we add them at the end. But technically speaking, we're all multiplying, right? So 9 times 8?
72.
72. X6 here, I have 6 of x, and I have another 6 of x. How many of them
12.
do we have?
X to the 12.
X 12. See, so it looks like we're adding, but technically we're still multiplying the whole thing. X times x times x times x, 12 times. Okay, so please don't make you get your confusion there. Okay, what about the y?
19.
And that's how we clean up this big mess. Questions on that? Okay. Here's your quiz.
Just kidding.
Yes.
Yeah.
All right, here we go. You don't have to write the problem down. I don't want to waste time. It's always online anyway. So, by the way, shh, the quiz is available right down here. Notice it's underneath that. Here it is. Just go and click on that. Here's the first quiz. Here's DMQ number 1. Go ahead and take it. Let me go ahead and stop this right now.